Hi everybody, I'm Peter Ruggiero from Oregon State University, and today I'd like to tell you about a project in which we've developed a stochastic emulator of the individual drivers responsible for extreme coastal total water levels, and how we're combining that set of drivers with high-fidelity numerical models of coastal processes to drive coastal flood impacts research. This title slide shows a partial list of the cast of characters involved in this work and the institutions that have been funded by CERTA. Now, while our goal is to develop methodologies and techniques that are applicable anywhere within the Pacific Basin, today I'm going to talk to you specifically about a case study at Naval Base Coronado in the San Diego Bay Area of Southern California. And so there's no real need for me to motivate the need for understanding extreme coastal total water levels to this crowd. But through our deep discussions with folks at the Naval Base in terms of engineers, practitioners, managers, etc., we came to understand that there's a lot of infrastructure on the bay side with piers and docks, etc., that have relatively low freeboard, as well as in the ocean side. There's a human maintained berm that protects the backshore infrastructure from coastal flooding. The naval base also has a desire to maintain a relatively wide beach for a variety of naval exercises. So there's a lot of concern with present day coastal flooding, as well as what conditions might look like into the future. Okay, so the objective of our work was really to develop a probabilistic approach to efficiently evaluate coastal flooding in both today's climate and under a range of possible future climates. The approach with which we took was basically to develop a hybrid statistical dynamical downscaling technique, which takes advantage of a broad range of machine learning and data science advances. Now I can spend a lot of time on the details of the methods, which can be explained or found in the papers in the lower left-hand corner of this slide. But in general, our approach combines three components. First of which was the development of this emulator, or TESLA, which is the time-varying emulator for short and long-term analysis of coastal flooding. And so this approach, TESLA, really takes advantage of the fact that coastal conditions that drive extreme total water levels are the result of synoptic-scale meteorological forcing, which is in turn a consequence of basin-scale quasi-steady atmospheric and oceanographic patterns. So therefore, we take a weather typing approach in which we are able to produce synthetic time series of the individual drivers of extreme total water levels that preserve both the marginal and joint distributions. And so we're able to use TESLA to generate an infinite combination of the individual drivers of coastal total water levels. Now we want to combine that information with high-fidelity numerical models of coastal processes. In this project, we have partnered with Patrick Barnard's group at the USGS and their Cosmos model for Southern California, which is a combination of Delft and Swan models as well as X-Beach models. And we think through a library of a finite number of dynamic simulations based upon TESLA output in terms of input conditions. And then we develop surrogate models that are machine learning based, with which we can actually pass now an infinite combination of the individual drivers through this numerical model in a relatively efficient fashion and develop time series of coastal flooding anywhere within the region of interest. Okay, so what can TESLA produce for us? Here's a record of synthetic combinations of individual drivers over a 10-year time period at hourly time scale that can be combined into a total water level proxy shown in the bottom panel. We can do this for 100 years. We can even do this for 500 years. We can do this for any number of combination of events we would like. And one thing, now we have this approach, we could actually pick off the annual maximum total water level produced by this range of combination of individual drivers. Using that set of annual maximum, we could also then combine that with a much larger time series of TESLA output to actually find a whole slew of different combinations that produce the 1% exceedance event, or the 100-year return level total water level event. And this really drives home the fact that not all extreme total water levels are created equal. In fact, there's an infinite number of combinations of things like wave height, period, storm surge, monthly mean sea level anomaly, all interfering with astronomical tides to produce extreme coastal total water levels at this and many other coastal locations. So once we have this approach, we can actually develop a variety of really interesting applications, combining with sea level rise and other climate change projections. We can pass that information through TESLA, through the numerical model, the surrogate models of the Cosmos model. And we can develop products such as the number of days in which we have water levels that exceed peer use thresholds. We can derive these kinds of curves for a variety of sea level rise projections at a variety of different time periods, and we can assess different aspects of the pier and Naval Base Coronado Ruggerio's infrastructure and determine whether or not it'll be mostly functional, partially functional, or even potentially not functional latter parts of the century. We have another potential application on the ocean side using the X-Beach surrogate models. We can actually determine the number of daylight hours that are available for the kinds of beach training that the Navy actually performs at this site right now. And we can actually identify thresholds and potentially even tipping points over which the beach width might actually become too narrow to perform these kinds of training exercises. So I'll leave you now with a couple of final thoughts, but just to remind you that we have basically combined dimensional reduction via Tesla, the climate emulator, computational reduction via these machine learning derived emulators of the model Cosmos. And with this combination, we can actually derive a wide range of coastal flood risk applications. Finally, I'd like to say that Tesla is available via open source code on this GitHub page, and I'd really like to thank you very much for your time and attention. Take care.